Hi, my name is Aditya. I am the CEO of Automatsky, and today I am going to be showing you how to crack RSA cryptography using the Shor's algorithm. The Shor's algorithm was made in the 1980s, 1990s by Professor Peter Shor at MIT, and it is the first algorithm that can be used to break RSA cryptography. RSA cryptography is what is used to secure the internet routers, switches, websites, banks, etc., and even cryptocurrencies and blockchains. So, what we have today is a small demonstration where I'll be cracking a couple of numbers. Before that, let me show you the source code. This is the source code of the Shor's algorithm implementation, which we have taken from Qiskit, and it is under Apache license version 2. And as per the requirements, we state here that this code has been modified by Automatsky. We have fixed some critical bugs with continued fractions and overflows, which were there in the IBM Qiskit implementation, because the IBM Qiskit implementation was never meant to factor large numbers. And once you try to factor large numbers, it gives underflows, overflows, and errors. So we fixed some of those. And instead of using the IBM's backend systems, we are using Automatsky's quantum computers, and we have removed the transpilation step. So except for the copyright of IBM over its work, the changes are copyrighted by Automatsky. Now this is a source code. I'm going to be very slowly scrolling through the source code. These are all the imports of Qiskit. This is how we integrate the Automatsky SDK and connect to the quantum computers. Now, Automatsky's quantum computers have uh, thousands of qubits available, and for smaller qubit sizes, we have a huge number of gates available which can be used. So this is a Shor's factoring algorithm, blah blah blah, and you are getting angles 5 gates because you need to construct a quantum Fourier transform and inverse quantum Fourier transform. So you're doing all this, and this is the code. And you need to calculate power of modulus n, etc. So this is what it does, and some validation. You construct the circuit here. You can see the QFT, etc. inverted and then converted into a gate, appended, etc. Modular inverse, and this is the routine where you classically get the factors from the Shor's algorithm results, which get executed over the quantum computer. This is basically continued fractions, and so it has a lot of issues, but uh, anyway, this is the code, and this is where we run it on the Automatsky quantum computer circuit. Repetitions is equal to 1000 shots, top k is equal to 20, which means get the top 20 results from the histogram. And here we are, we declare the backend Automatsky quantum computer running on this IP address and port number 80. Instantiate the Shor's algorithm with the backend, and n is the number we are trying to factor, and a is a parameter used in the circuit. Usually we try with a is equal to 2 or 3, 5, 7, etc. And that is used for period finding and continued fractions. And then we actually factor the number and we print the results, which is basically the two factors, to the screen. So let's run this. There is no hanky panky here. This is running on Automatsky's quantum computers, and you've seen the source code. So let's run this. So 21 is the largest number factored. Uh, I think 35 is the largest number factored. 21 was before that. So let's try 21. And the system is going to print the number of qubits, logical qubits it's using, and the number of gates in the quantum circuit. So to factorize 2021, we are using 22 qubits and 64,151 gates. Give it a couple of seconds, and there is the output. It took 12.538 seconds, and the number we're trying to factor is 21, and the solution is 3 and 7. Now 35 is the largest number factored so far by pure Shor's algorithm without using any trickery. So see, I'm not going to be even talking about hybrid algorithms and classical algorithms, etc., because that is, beyond the point of this, demonstration. So we are trying to factor n is equal to 35, and this is the largest number factored ever using Shor's algorithm on quantum computers. There are no quantum computers in the world which can do more than this. And for this, we are using 26 qubits and 1,17,421 gates. Give it a couple of seconds. It should, yeah, and the number we're trying to factor is 35. It took 14.34 seconds. And the solution is 5 and 7 here. This was 3 and 7. And this is 5 and 7. 7 fives are 35. 3 sevens are 21. So that's our solution. This is the biggest number. If we can crack this, this will be the biggest number ever cracked by Shor's algorithm. 13 into 17. Let's run this. So this the Shor's algorithm implementation takes a lot of time, and creating the circuit, transpiling it, and handing it over to the quantum computer, which also takes a couple of seconds, and then back, to process the results of the quantum circuit. It takes a classical routine that is also very expensive computationally. So for large numbers, it takes a lot of time. So 13 into 17, we are taking 34 qubits and 3 lakh 13,169 gates. Give it a couple of seconds. There is a scheduler also, and the payload has to go over the REST API across the world, and the solution is here. 13 into 17 is 221, and the factors are 13 and 17. So 221 is the largest number factored so far by any quantum computer in the world today. And this is all we had to show you today, and thank you very much. If you have any questions, please reach out to us at info@automatsky.com. Hope you have a nice day.